Alright, welcome again, and this is a little bit more extension work, but it can be obviously going to help us answer our test questions and help us think about how heat energy moves through our environment and the problems that come with that, which is where we're heading for. We're going to look at this whole idea of how it affects our climate and how it affects our lives. Now, I've chosen this photo very nicely because if we think about it, there is a heck of a lot of the earth that is covered with water, and water is a very, very good storer of heat. I always love this picture from space of our planet, and that's why we call it the blue planet. And we can see that we've got the surface mainly covered with water, but we do have continents out of there. And every day since the earth has been here, and every day since the oceans have been around, we've been absorbing energy from the sun. And it's pretty consistent with the amount that comes each day, as we'll see. But not all of it comes back. In some planets in our solar system, heat goes in, and then the same amount of heat comes out of at night. Now, you have already done work on the Earth's energy budget, and we see that actually less comes out than comes in. So we're actually having a net gain of heat energy by our planet. Alright, now this I quite like this. It came from NASA, and it shows in not as detailed as what we've already gone through about how much energy comes in. So if we've got a light and heat coming from the sun, or radiant energy coming from the sun, we can see some of it is absorbed by the air, some of it is reflected back into space, and some of it goes all the way through, and that's almost half of it. And according to the figures I was able to find, we find that 340 watts per square metre every second. That's an amount, alright? So that means the same as 340 joules per second is arriving at the top of the atmosphere, and this is going through. And as we can see, even half that amount, considering how many seconds are in the day and how much heat comes into it, that's a heck of a lot of energy. Alright, so let's look a bit more closely at these types of water that's available on the earth. And we see from this one, this is a breakdown, and this is a bit of a problem for us, but it's not a problem also. We've got most of the water is tied up in our oceans, almost 98%. So about 2.5% are tied up as more freshwater than saltwater. Now, we do find that the salt has an effect on the physical properties of water itself. For example, we see that it depresses the freezing point. So this means that water with salt in it will not not freeze at 0 degrees. It will freeze at somewhere below 0. Right? So it pushes the freezing point down. And you might have seen this when people go camping back in Australia. We find that they take an esky or a chilled bin with them, and they put ice in it. Now, to stop the ice from melting and warming up the food that they carry with them for their camping trip, they put salt on the ice. And by adding salt to the ice, it actually keeps the ice in solid form, so it keeps it cooler for a lot longer. We also find we've looked at a thing called specific heat capacity, and if we look at them, there are two numbers down the bottom. 4186 we know, joules per kilogram per Kelvin degrees, or Kelvin, and that's for pure water. The one above it, 3993, is for salt water. So we can see that adding salt actually lowers the ability of water to store, but not by much. It can still store a lot of heat. Alright, so if we think about the basic things, we're going to find salt water heats up faster than fresh water. This might explain why if you've ever been swimming in saltwater and freshwater, you notice that the freshwater always seems to be a little bit cooler, a little bit more refreshing. Right, seawater still requires a lot of energy. I'm just going through these to raise its temperature by 1 degree. But the big thing is, we've got so much of it. Now look at that one. We've got, let's put in some marks here so we see what's going on. I'll just use the black pen. Put in these ones. So we've got, according to this information, we've got 1,338,000,000 cubic kilometres, like a kilometre cube, a kilometre long, kilometre wide, kilometre deep, cube of seawater on the Earth. So that amount simply means that if we're raising the temperature, we're taking in an awful lot of heat. And as we can see, this equates to that many kilos. 1.35 times 10 to the 21. Now, 10 to the 6 is a million. 10 to the 12 is a million million. 10 to the 18 is a million million million. So that means we are looking at 1,000 million million millions of kilograms. So let's have a look at this. Now, in the US, there's a government organisation called the National Oceanic and Atmospheric Administration, or NOAA for short, and they've been keeping monitoring over the Earth and the Earth, the oceans and the air. That's their job. So they've got lots and lots and lots of measurements they can take, and most of them are to do with temperature, and they keep really, really good records. Now, their records show us that the temperature of the oceans has increased by 0.13 degrees C. That mightn't seem much, but let's think about how much that really is, because the oceans are so huge. And if we're making the whole of the ocean increase by 0.13 every decade, this is an average, by the way, then over the 100 years, we're looking at 1.3 degrees C. Now that mightn't seem much, but let's actually work out how much energy. So we'll go to our Q equals mc delta T. So I'm going to convert everything into its forms that it's supposed to be in. We've got mass in kilograms, done. We've got the C value of salt water, I'm using salt water, done. And we've got temperature change, done. So let's put it in. So it's 1.35 times 10 to the 21 times 3993 times 1.3. Now, according to my sums, that is this number. Or as we're going to say, 7.01 times 10 to the 24 joules. Now, you know that prefixes we have, like if it's 10 to the 3, it's kilos. If it's 10 to the 6, it's mega. So scientists have given this one a big number, like a lotter number, except 10 to the 24, 10 to the 24 is actually given the name Y, which stands for yotta. So we're finding we've got 7.01 yotta joules of energy was required to do that raising of the temperature of our oceans. Now, when you consider that is a million joules, 7 million joules. That's a lot. Alright, more about this later.